Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you.
How do I look?
Cool.
Do I look like Jenny got me a new shirt?
As good as it's going to get, I guess.
It's hard to improve upon this, isn't it? Understand.
It's something. It's something, man. You got something going on over there.
I do. I know. I know. I got an update on my Fight Club status. Still holding strong.
Oh yeah. Okay. That's good.
It's a dang good thing it's a virtual Fight Club, I'll tell you that.
No. Yeah.
Yeah. You know, I want to ask you this. I'm thinking about changing the name of my class.
Why? Give me the pitch.
Because, what?
Give me the pitch.
Oh, that's not what I thought you said. Because I don't know. I just think that geology is more old school, I think, and geoscience is more, it has a bigger umbrella, I think. Does that make sense? What do you think? Should I?
I think that's right. I don't know. I'm of two minds about this. First of all, our department at Penn State, I mean, I had no say in this. When I showed up, they had already changed the name to Geoscience. That had happened a long time ago. But I think it's a good name. I'm always a little suspicious of name changes that departments do. And it was, I don't know, maybe 10 years ago is a really common thing for geology departments across the U.S. to change their name in kind of a rebranding to like earth science departments, or earth and planetary science departments is now a very popular one. And I think it makes some sense when you start hiring people who study Mars.
Yeah.
That maybe are, hyperspectral experts and not geologists. They're kind of like, the name doesn't fit me anymore. The name doesn't fit us very well anymore. So it makes some sense. And I think you're right. Like, I think it's whatever new students associate better with with like what they want out of the degree program, right? I'd be curious. It was really interesting. I was reading through Rachel. So we talked to Rachel Phillips, and I was reading through her grant proposal. She's putting some big grant proposal together, and a lot of her work, she's kind of coming up against this really weird statistic. I want to get her on. We should talk to her about it again.
The misconceptions around geology and geoscience, right? Yeah.
Geology was like the lowest, I'm probably misquoting, but like geology was among the lowest science disciplines, STEM disciplines, for what students thought were kind of sustainable or good jobs for the environment, or like people who cared about the environment. And that kind of shocked me, because every geologist I come across and know is like, they love the outdoors and love the environment. It's not like a kind of a rape and pillage mentality amongst geologists, but the perception is that. So if you change it to geoscience, it might be different.
Well, so she said that. I think she did a poll, right, of your feelings about the word geology and what it encompasses, and then geoscience was really quite different.
Way different.
And that's what got me kind of thinking about it. I don't know. I think I'm going to do it.
I think it's a good idea. Why not?
I'm going to rebrand Chris's geoscience class.
I'd be curious to know what the students think about that. You should ask your students. I'm going to ask them what they think about the difference between geology and geoscience.
Yeah, it's a good idea. I got to come up with a way to frame it. I want to have them provide feedback, or maybe have them like, what words do you associate with geology and what do you associate with geoscience?
Yeah, right. Gotcha. Yeah, that's a good one. Yeah, that'd be interesting to know. Cool.
That. I'll stay tuned. I'll give you an update.
Stay tuned. Yeah, give us an update. I'd be very curious to hear that. That's super interesting. Okay, Chris, today, this is chapter, what are we on?
Well, I don't know. We're on our fourth or fifth kind of episode that surrounds Earth's Chris, oldest materials.
This is number 6, actually. We've done 5 of these already. Yeah, this is number 6. And so we're ripping through these things. We're going to talk about the Isua Greenstone Belt. That's ISUA Greenstone Belt. This is up there. It's probably more famous than Acosta as a location.
Does that hurt you to say
Earth.
That? Does that hurt your heart a little bit?
I think so. It's really interesting. This is they're all so different, Chris, all these locations that have old rocks. Isua was kind of one of the first. It was discovered in the 70s or 80s, this hints of old rocks, and it's been studied since then. I mean, there have been so many papers published on this stuff. These rocks here, they've been the focal point of a lot of research, and you'll hear it called different things, and the point here is just to give a really high-level overview. I'm not an expert on these rocks. I know old rocks, and I pay attention to this literature. I've not read every single paper on Isua. It's just, that would be a really hard task. There's been so many papers published on these rocks, but there's some commonalities between these rocks and other ones that we can get into, and this is going to be a pretty high-level overview of the geology of this suite of rocks. So this is Southwest Greenland.
Real quick, pronunciation-wise, are you saying Isua or Isua? Because I've always said Isua, but I feel like I'm getting an SH sound.
No, I think it's Isua. Isua or Isua. You'll hear it pronounced differently, but I would say Isua. Yeah, Isua makes the...
And just for perspective, image number 1 here shows the location of where this is found, where this rock suite is found. It's Nook, right? Is what it's
Nook. Yeah, I think some people give it a harder U, but yeah, Nook. Down there near this region, this village, and this has been discovered, a long time ago. The history of these discovery things is always kind of interesting, but it's mapping before the days of really, really quick geochronology that we have now. So, getting a date from a rock was a really difficult thing. Hints of these old rocks. First thing, Chris, this is going to be chapter 6 in our Earth's Oldest Rocks visual podcast series. So you can get the images here in audio form on the app. Go to the CampGeo mobile app. First link in your show notes. So what we've got here, Southwest Greenland. You'll hear this referred to as Southwest Greenland rocks. You'll hear this referred to as the Isua Supracrustal belt, the Isua Greenstone belt. There's many names that kind of relate to different parts of this, but it's an area along the coast that's not covered by the Greenland ice sheet. Old rocks down there in the south.
Yeah. Do we have any idea how extensive this Greenstone belt is?
Yeah, actually. So I'm going to skip ahead to this image number 2 here real quick. And image number 2 is a map this is a very, very simplified map. So I took the base geological map, which is more complicated, and I super simplified it. All we're showing here in these different frames is kind of as we zoom in to the rocks here. First of all, you have ocean with fjords, and then you have yellow land, and then I've also shown where the extent of the ice sheet is, and so the ice sheet is shown there as well. The orange rocks are an old series of rocks that's called the Itzhak Gneiss Complex, and that's kind of, you can think of that like the Acosta Gneiss Complex. These are old metamorphosed igneous rocks that are like 3.7, 3.8 billion years old. And they're really deformed, they're altered, but you can map them out, and it's kind of disaggregated. You can see this, it's kind of broken up. It's not a continuous exposure. It's exposed in kind of bits and bops everywhere in this area in a big linear belt. And then I'll just note that the Isua Greenstone belt, the old rocks, what these are an inclusion in the Itzhak Gneiss Complex. And Chris, what do we know about inclusions in rocks? How do we think about inclusions?
Yeah, it's a basic principle in geology that the inclusions are older than the rock that they're in. So this is the oldest of the old, basically.
That's exactly right. So if this Itzhak Gneiss complex is 3.7, 3.8 billion years old, the oldest components in there, and it cross-cuts the Isua Greenstone belt rocks, the Isua rocks are an inclusion in it, then Isua Greenstone belt, the Isua Supracrustal belt, must be older. So these are kind of rocks that we can put a minimum age on. We don't necessarily have a maximum age that I know of that's very clearly defined, but they're like 3.85, 3.9 billion year old rocks.
Okay. Hey, so it looks like all indications are that it does continue under the ice sheet, right? We just don't know how the extent of this, like from a lateral standpoint, right?
Yeah, that's a good one. I don't know exactly where this ends. I've not been to this region, so I don't know exactly where the ice sheet, ends. There are almost certainly old things exposed up underneath of the ice sheet, and there's been one study, actually, I'd have to revisit it. I haven't read it in a couple years, but there's been one study where they took stream sediment samples and looked at the detrital zircons that were being eroded from under the ice sheet. I mean, we talked about eskers before, and I think eskers are like a really interesting exploration tool. And this was kind of doing that in the modern setting. So they got some old ages from up under the ice sheet. So there's old stuff up there, Archean, Mesoarchean, Paleoarchean, these old rocks, but not clear that it's older than the Isua Supracrustal package. So yeah. So just let me run through those names again, because they get confusing. So what we're focusing on here is the Isua Supracrustal belt, or also called the Isua Greenstone belt. That's the super old stuff that people focus on a lot. The broader complex, the Itzhak Gneiss complex, those are metamorphosed igneous rocks that are, comparable to Acasta, except younger. So they're like 3.8, 3.7 billion years old. And then this whole region is kind of southwest Greenland. It's part of the North Atlantic Craton, the Nain province. So you hear different words that kind of refer to different packages within here. But the point is that there are old gneisses, and the Isua Supracrustal belt is a inclusion in those old gneisses, and that means it's older. So,
hey, I think, Jesse, let's back out of this a second before we get into the specifics of the Isua and why this is so important and so extensively studied. Let's talk about greenstones in general. Because geologically, greenstone, we call them greenstone belts quite often. They're not that uncommon, right? And they're almost always old. A lot of them are really old within the Precambrian. Really yeah.
So, Chris, I remember you describing greenstone. And did you have an alternate word? Did you used to have an alternate word for greenstone? Yeah, what is it? Remind me what that is again.
I just called it a metabasalt. Yeah.
Yeah. Okay. Yeah.
It's
that's
okay.
Right.
It's like, it makes more sense to my students, because
for sure.
So young.
That's all it is. That's simply what it is. So basically, I remember going back to the Menards, the famous, what used to be the outcrops behind the Menards.
So ticked off about this. So ticked off.
Regular listeners of the podcast will have heard this one before. But yes, these things occur in a lot of different places. And the ones we went to, where was that, Chris?
It was
the UP?
In Marquette County. And so this is on the Lake Superior side of the Upper Peninsula, basically, for those that aren't, all that familiar with what we call the UP in Michigan, the Upper Peninsula. It's just, they were beautiful, Jesse. You're hard pressed to find like more striking and like really, really good looking pillow basalts, metabasalts. You get it's like this perfect area to just sit and talk about a lot of like really important geology concepts, it's just really, there was so much there.
It's really cool.
Dynamited it to make room for a bigger lumber yard. It was so mad.
Bummer. The thing about these is that they're everywhere. And so, up there, it's around Ishpeming, right? It's a package of metamorphosed basalts. We call them greenstones. That's kind of the shorthand for them, especially in Archean geology. Those ones, Chris, up there are 2.7 billion years old, which is a really common age for greenstones globally.
Why is that, Jesse?
Belts.
Why is 2.7 the number? We've talked about this a little bit before, I think, we talked about like the evolution of continents and so on, right? You get a lot of ages that kind of fit in that timestamp.
Yeah. So this is a big peak. Well, it depends who you ask, but this is as usual, as with everything, especially when we go back in time.
But we're asking you, the resident doctor in the house. Me. Okay, I'm asking you. I don't care about everybody else.
Fair enough. What we do know is that at around 2.7 billion years old, we start to have a lot of rocks preserved on Earth for the first time. Like we have a lot of areas that have stable cratons are forming or being stabilized around that time period. And so you could argue that that's a crustal formation age, that actually crust is being formed in a large volume at 2.7 billion years old, or you could argue that it's a preservational thing, that there's some processes that are creating a preservational bias for that time period. And those are two sides of kind of the same coin, but the point is that cratons stabilized, these big blocks of continental crust that stabilized and became basically, they don't get deformed for billions of years after that. And so all the rocks that are in that region get preserved. And a lot of them are these 2.7 billion year old metabasalts. But the important thing here, in this image number 3 here shows this really well, is the pillowed aspect of these. And Chris, pillows are one of the coolest phenomenon out there. They're
Hands
just
down.
as far as what you could, a geologically observable phenomenon. Like look at the rocks, you think, holy crap, this is a beautiful feature, and it tells you stuff about the rock.
So, Leah, let's talk about that a second. But before we talk about pillows, Jesse, and what that means, let's get into the detail on that. Why not, right? But I want to ask you this, though. When we talk about a metabasalt and the age of it being 2.7 billion years, are we talking about the origin of the basalt? Or are we talking about the metamorphism that... So are we looking at the rock that it turned into? Or are we talking about the original volcanic rocks that got metamorphosed?
It's a really good question. Usually, in almost all cases, we're talking about the original formation age of the rock. Okay. So 2.7 is the eruptive age of these pilobasalts, of these metabasalts, of these greenstone belts. And so the formation age, and then they're metamorphosed, but they're usually not metamorphosed that much. And here's the key for the greenstone part, is that these are metamorphosed to pretty low grade. It's like it's chlorite is the main mineral. So you take a lot of the basaltic minerals, your typical basaltic minerals, you turn the feldspar into sort of sericitize it a little bit, but it's still feldspar. And you take a lot of the amphiboles and turn them into chlorite and a couple other low grade minerals.
Chlorite is this kind of green, like various shades of green. It's a beautiful rock because you get this greenish black. And to me, Jesse, it always kind of looks like a smearing of green over top of the black.
That's exactly right. And so it's a low grade metamorphic event. It's definitely we call this a green schist facies metamorphism because it creates this green rock. And it's a lot of chlorite. So this is like low temperature, hydrothermal, couple hundred degrees centigrade, variable pressure. This could have happened, at a mid-ocean ridge setting, kind of, maybe a little bit higher grade than that, but that's what's happening here.
So what else indicates that this would be a mid-ocean ridge kind of setting where you would get this is the fact that you have pilobasalts. And that's what I love about pilobasalts or pilolavas is the story that is locked up in that rock. You can get so much information just from almost a cursory, just a short glance at it, because the only way to get these pillow structures is to have lava that erupts out onto either an ocean bottom, so a mid-ocean ridge, or, you can get this in lakes, in more of kind of this niche setting, but you have to have lava that's erupting into water. What you have then is you get this very fast cooled, almost like a rind is how I refer to it, like a watermelon rind, if you will. You get this like inch or so shell around this rounded structure, but the lava that is underneath that cracks the rind and a new, lava pillow squirts out and the process just repeats again and again and again.
It makes beautiful rocks, but that rind character, the rind description is really good because you get this really rapidly cooling rind, and then a little bit you get coarsening of the rock as you go into the pillows. And the key feature here is that these are basalts erupted into water. That's the key observation. And a lot of these things in that 2.7 billion year old age interval, a lot of those pilobasalts erupt through older gneisses, and so they're erupting through what used to be kind of a continent-like thing, but they're still underwater. And so that old gneiss package was submerged beneath sea level. These basalts erupted into it. And sometimes these can be really thick. In the 2.7 billion year old rocks, these are really thick. They can get to kilometers thick packages of basalts. They're really important for economic resources, huge amounts of gold in these areas, lots of other metals that we mine from these regions. So they're good targets for exploration. And this is what gives the term, there's a very classic term for Archean blocks of crust that are called granite greenstone belts. And the granite is these granite intrusions. We've talked about Earth distilling itself and melting. And then the greenstone belts kind of surround the granite. The granite kind of intrudes through the greenstone belts, which is a later event. And that's very common that's very typical Archean geology in cratons globally. That's not that is kind of what we're talking about here. Just Isua is a very much older version of this. It's 3.9 billion years old,
which is
at least.
That's amazing to me for this reason, really, is that, first of all, that's a staggering number that we have rocks that are that old, but that's what we're talking about, Earth's oldest materials. But Jesse, this means then that because you have pillows, that you also had oceans at this time, right? And that's I don't know. Let that sink in a minute, right?
Yeah, it's so cool.
We had oceans on this planet that are really, really, really old.
Yeah, really old, unbelievably old. And if we refer back to our 2 episodes on the Jack Hill zircons, those little zircons contain isotopic evidence for oceans going back even further than that. So we've had oceans for a long time. We keep kind of pushing the limits of these things, going back and back. The more rock record we get, the more observations we kind of get that there was surface water. We'll talk about this in this episode here. There might be evidence for life in these rocks. So there's really, really the more rocks we have, the more evidence we can accrue to tell us about how the planet looked back in time. And these, Chris, are really interesting because you talked about water being around. The next package of rocks, or really, if this was just a greenstone belt, it wouldn't have received as much focus as it has over the last 50 years, this Isua Supracrustal belt. But the Supracrustal is above the crust. I mean, that's kind of what that means. It's above, sits on top of the crust. So usually these are volcanic rocks that are erupted onto the surface and sediments that are interspersed. And this, just like the ones you took me to in high school up in Ishpeming there, we have banded iron formations layered in amongst the greenstone layers in this supracrustal package.
Yeah, it's a geologic mess, Jesse, to try to work this out, just in terms of the principles in geology of, relative dating, just doing that. I mean, that was one of the things that we did when I took you up there as a young student is, we went to this beach and had to work out. This beach is a part of that greenstone belt, runs through the UP, and working out the geology. It's just a great mental gymnastics exercise to apply these just awesome principles. But Jesse, I want to ask you about this because you have this package, this suite of rocks that includes volcanic rocks, basalts, sediments, and gneisses. All of it's super old, but how did the sediments themselves, the sedimentary rocks, were they metamorphosed to in Isua? They're not still just sedimentary rocks?
No, these things will have been metamorphosed as well. And these things get metamorphosed. This is what makes them complicated, and this is what makes them difficult, and this is where all the scientific debate comes from. That is so frustrating at times because we have a lot of ideas. We don't necessarily know for sure a lot of stuff. And that's frustrating, right? I get frustrated by that.
It is frustrating. So what
hard and fast things, but they've been metamorphosed multiple times.
What are the debates that kind of surround the Isua?
Yeah, so most of them, the ones we'll highlight, there's many debates, but the ones we'll highlight, the ones that I think most people who might listen to this podcast may have heard of, are ones surrounding evidence for life. And so just imagine a scenario. I'm going to paint a very kind of simplistic picture of how this stuff formed. We have a setting that's in a shallow ocean environment. You have basaltic eruptions happening that are putting these basalts under the surface. Pillow basalts are forming, but in between the time when the volcanic eruptions are forming and the basalt is flowing out onto the surface, in between that, you're going to have deposition. And so we have these banded iron formations, chemical precipitates. Speaks to a very, very different world, the banded iron formation, the fact that these are being deposited, and there's debate about how those actually form, but it's a very different ocean chemistry that's dropping these things out. And so then you have another basalt eruption that covers up the banded iron formations, and then after that quiets down, then you have more banded iron formation getting deposited or more chemical sediments getting deposited. Maybe there's a little volcanic arc that pokes its head up above the surface nearby, and there's some sort of gray wacky like sediment that washes that sediment down in thin layers of gray wacky type.
Let's explain that a second.
Sediment.
Maybe some listeners haven't heard of what gray wacky is. So we call it gray wacky, or sometimes just a wacky sandstone. And this is a poorly sorted sandstone that you get in kind of very niche settings in geology. It's not a super common rock at all. In fact, I decided to remove it out of my set of rocks that I have my geology students identify.
Oh, really? Okay.
Yeah, I did. I took it out because it's so niche and they were never getting tested on it. And so I just removed it just to make it a little simpler and faster. But, you get this like in turbidity currents and things like this that sometimes rip down continental slopes, or as you said, where you'd have this sediment washed off these arcs maybe, and you get rapid deposition. And that's really the only sorting that you get is the heavy stuff settles right away, and then the finer grain stuff takes a little bit longer to settle, and that's really the extent of this sorting because in this erosion process. So yeah,
that's right. And so these things they're actually these types of wacky type rocks are more common in the early Earth than they are today, or at least proportionally. They're proportionally more common, and the various arguments about that. But either immature continents. You don't have huge Mississippi-style drainage basins forming. You have more island arcs popping up and getting eroded down. Or, it's a preservation thing that these are more likely to be preserved, whereas huge, pure quartz aeronites are more likely to be eroded. And it's proportional. We just don't have that many rocks with which to assess this, so that of the things we see, they're proportionally more, but we don't know if that actually is statistically meaningful either. So,
right. Okay. So back to the controversy with life and whether or not that's what's doing this, right?
So there's a couple different. There's basically two different pieces of evidence that people there's more than that, but two main ones that people have argued are evidence for life in these sediments. Because you think this sediment thing is happening, the ocean's there, this might contain a record of early life. And if we're looking for old life, we're going to find it here, not in rocks like Acosta, because Acosta has almost all igneous rocks. There's no sediments in there. There's no surface basalts that we know of. There's no really clear pillow basalts in Acosta. So here is the place you would go to look for life, for signs of ancient life, because these rocks were formed in that near surface environment, and some of them are precipitated right from the ocean or have interacted with the ocean. So we've got a couple different rock types here. There's these banded iron formations, first of all. There are some quartzites with like calc silicate schist. Those are kind of the gray wacky stone type things that are going to get metamorphosed together. So we have these calc silicate schists, and we also have these quartz rich rocks that are banded together with carbonates. So these kind of carbonate rich things, these quartz rich things, they've all been metamorphosed a lot. So there's a lot of discussion about what these things sort of actually are or actually represent. Some of them contain graphite layers. So image number 4 here, I'll skip ahead to this BIF. This is a graphitic BIF. So there's a lot of graphite in these things, and graphite's carbon, and carbon is essential to life. So it's interesting to figure out what these things might be, right? If you're looking for old life, you're going to go look at these things because there's carbon in these rocks, there's graphite. We're wondering what are these things, right?
And because Jesse, I don't think the debate is still settled in terms of how BIFs are laid down. These alternating layers where it's really iron rich, and then then you have silicate minerals, and then back to iron, and so on. They keep flip flopping back and forth. Whether these were aided by photosynthetic organisms that were providing the free oxygen that allowed iron to precipitate, right? But that's not the only evidence for life, because there's also these carbonate rocks that have a lot of magnesium and calcium carbonate in them, like a dolostone, if you will, or a dolomite that has stromatolites in it, or what we believe to be stromatolites, right. And that's another piece to...
Yeah, and this is my reading of this literature at the moment. So first of all, the back to the graphite thing real quick. There are graphite layers. You can use the carbon isotope composition. And so carbon has a couple different isotopes. The ones we care about here are 12 and 13, different number of neutrons in the nucleus. And life has a very, very, very prolific at fractionating these isotopes, at selecting one over the other. And so if you look at the carbon isotope composition of the graphite, either in these banded iron formation layers or actually as a little graphite piece or a little carbon rich inclusion in, let's say, an apatite grain, you can measure the carbon isotope composition of that, and a lot of these come up very low, -15, -25, -30, really low, which on the modern Earth, we would say, oh, that's clear evidence for life because life is really good at making low carbon isotope values here.
Okay, so hold on. Let's make sure that we double click on that. When you say that you're looking at carbon-13 to carbon-12, life prefers what?
Well, there's a couple different reaction pathways that will make it light, make it low, make it have more 12 over 13, which in our nomenclature just means it drives the value down because we're talking about a normalized value here. So it just makes it negative, very negative. So Chris, what people have done have looked with, huge, what are big mass spectrometers to make little tiny spots on these carbon rich grains, huge room filling mass spectrometers, measure tiny little pieces of carbon, measure the carbon isotope composition, and see what it is. And there's an argument to be made that this is life, that this carbon isotope composition on the modern Earth, we'd have kind of no problem interpreting it as life. However, when we go back in time, there's more debate because we don't actually know if there's life around 3.8 billion years ago. So to my reading, this is still contested space. Some people would say, yes, the simplest explanation is that these carbon isotope values in these rocks are indicative of life. The nail's not in the coffin yet. There's other people who would say that's not clear evidence for life. It's a possible explanation for these values, but you can generate low carbon isotope values with metamorphic fluids and more complicated pathways, more complicated stories. So it's an open question what these carbon isotope values actually mean, or at least it's a challenged idea. The stromatolite thing. So if we go down to these stromatolites, you mentioned it, that we have these like magnesium and carbonate rich layers, magnesium and iron carbonate rich layers. This is what a stromatolite looks like. You can envision this, Chris. Like you see stromatolites on the backside of the Tetons. Is that right?
Oh yeah, for sure. They're beautiful. Yeah, absolutely. Glacier National Park right? too.
Yeah.
In the Helena limestone. Right? Oh yeah. Oh, it's in there. You have these different colonies, with the way they stack up. Sometimes they look like cabbage heads, and different types of stromatolites will look like stacked construction cones. And, you get these like beautiful, intricate patterns in the rock. These are Earth's oldest known fossils. They're just blue-green,
spectacular
photosynthetic algae, but they're,
these kind of algal mats growing on top of each other, creating these layers. And there are people who've argued that they see structures that are stromatolites, again, in these sediments that are interlayered with the mafic volcanic rocks, with the metabasalt package, the Greenstone package. They're interlayered in there. There are people who would argue that these are stromatolites. That's been proposed relatively recently, like in the 2010s. And then there's been a bunch of work that also argues that this is just very complicated metamorphic deformation. And so you could imagine, and I want to kind of visualize this a minute, like if you have a package of metamorphosed of basalts with pillows in them, you have sediments layering in between them, the sediments are kind of draping off of the basalt flows. Like imagine the picture in your mind, a mid-ocean ridge setting or basaltic eruption, a volcanic flow top under the ocean, and then sediments getting laid down on top of that. It's not a beautifully clean boundary. It's not beautifully flat. It's going to be wavy and deformed. Then you take that thing and you metamorphose it and you stress it over a couple billion years, a couple different times. The basalt is going to deform differently than the sediments do. The way that the stress gets partitioned into deformation in the rock dramatically differs between these things, and it gets really complicated very quickly. And so I think that the stromatolite argument is not well accepted. To my reading, it's not a well accepted argument, more widely disputed, whereas the carbon isotopes and the graphite layers are more, 50-50 or perhaps a little bit more of a consensus view that might be life. The stromatolites is an interesting discussion. It goes back to kind of how you interpret structures in really complicated rocks. You can imagine how this is difficult. Like it can be frustrating to hear, oh, it's controversial. It's like we don't know. But that points to difficulty. I think when that happens, I think you can think we're really pushing the limits. This is cool because we're pushing the limits scientifically here. It's controversial because it's hard. It's hard to go to these rocks and figure out, is there life there or not? That's a big question. Was there life 3.8 billion years ago? Like when was the first time that we have evidence for life on Earth is a really important question. And so of course there's a lot of debate about this because we're pushing the limits. We're not just sticking to the easy interpretations. We're going out there on a limb and saying, this might be where it is. We're looking for scarce, scant evidence and trying to piece the story together.
So I understand that. It's so interesting when I look at all of this, the whole Isua complex, if you will. It's so similar to what you see in the Upper Peninsula of Michigan. I mean, every single thing. You have the metabasalts you have pillow lavas, you have banded iron formation that is world-class banded iron. It's so beautiful. And you have also stromatolite within the Kona Dolostone. I don't think I took you there because, it's a quarry now. And but I have taken classes there, but they charge us to go in. I think when the last time I went, it was like $150, and they let us go in and collect whatever we want. It's a beautiful rock. It's a cherty dolostone. It's got a lot of pink minerals in it. It's just gorgeous, and it has these intricate stromatolites within it as well. And so it's just like, it's so striking that every single thing that we're looking at here with the Isua is something that you see in the great state of Michigan too, in the Upper Peninsula, the Greenstone Belt.
This is the amazing thing about the Archean world, is that we get a lot of these. 2.7 billion years old. There's a bunch of greenstone belts, much like the ones up in Ishpeming that you go to. There's a bunch of those around the world. What's spectacular about Isua, and actually the one we're going to talk about next chapter too, when we talk about the Nuvuagatuck Greenstone Belt, is not that they're spectacularly unique rocks. It's that they're old. And if you think about the rocks that are here, we have metamorphosed basalt, we have sediments. Both of those are really hard to date. Really hard to date with traditional. They don't crystallize zircon. It's not like you can extract zircons out of the basalt and date them. I mean, you can because there's metamorphic ones in there, but they give you young ages. You don't know what that means. It's a metamorphic age. Clearly, you don't know the crystallization age still, or the eruption age.
What you mean is you're not going back through the metamorphism to the original rock, to the age of the
exactly. And these rocks have been metamorphosed a bunch of times, so they get more complicated every time you metamorphose them, and you erase more of the initial signature. So it's just I just want to frame how cool this is that we have water-laying sediments and basalts that were erupted under the ocean that we know are at least 3.8 billion years old, and in those rocks there are hints or potential indications of life in the carbon isotopes or in the stromatolites. Maybe there's a lot of debate, but we're pushing the limits. We're seeing through 4 or 5 metamorphic events to see that these were not only laid down in the ocean, but see what kind of chemistry there was, the banded iron formations, the different types of sedimentary rocks that are being deposited. And then we're having a debate about, whether there's signs of life in this. So we're really far along in the geological interpretation of these rocks, given that they're so old. It's impressive. I think it's impressive that these things get discovered, and there's a reason people study them so much.
That's right. And that's why this is such an important suite of rocks, is that there's so much to learn from it. Was there life at this point? If we can establish the age of these rocks pretty well, and you feel very good about that, right? 3.8 billion years old.
Yep. 3.8, the sediments,
there's not debate in that, right?
There's not a lot of debate. Yep, that's right. They're in that range, 3.9 billion years old. Yep.
Then knowing that age, then if we can answer these other questions, those are really important things to know. Was there life at this point? What was the ocean like at this point? And who knows where it goes from there, right? Atmospheric implications, exactly right. and it's just so much to learn from this suite of rocks.
Yeah. And so Chris, so maybe we'll just end as a lead into the next episode, or kind of a cliffhanger for the next episode, which we're going to talk about another package of supracrustal rocks, kind of very similar rock types, except the age has been suggested to be 4.25 billion years old. There's debate about that age, but it's another one we got to talk about because it's very similar to Isua. It could be the same age as Isua, or it could be 300 million years older than Isua. And so the age is the debate here. When you get to these rocks that are this old, there's different ways you can kind of calculate the age. We're going to talk about the age debate on what might be the oldest rocks on Earth, than the Nuvuagatuck Supracrustal Belt up in Quebec. But you kind of have to think it's kind of the same type of thing. It's basalts, it's banded iron formations, it's some chemical sediments interlayered together in this complicated package of rocks. That's a very similar story across most of the Archean when we get this record.
Okay. Hey, quick question then. So we learn different things studying the Isua than we learn when we study the Acasta, right?
Yeah,
we're looking
right.
at different questions.
Different
right?
processes. Yep, exactly. Yeah, for sure. In Isua, because these rocks are formed in the near surface environment with oceans around and water around, we're looking at surface processes. We're looking at maybe there's life. We're looking at what's the climate. We're looking at what's the ocean chemistry, that kind of process. In Acasta, it's much more, these are igneous rocks, magmas that crystallized. It's much more kind of how did continents form? So that's kind of like how did the continental crust form? Here we're looking at what was going on between in the surface environment, the near surface environment in the ocean. And so what you can do is if you find, and this is very common across all the old rock locations, if you find older stuff, you can just take the same suite of tools that we've applied, the same kind of scientific methods, the same toolbox, and you do it again, except older. So when Acasta was found, I wasn't around, but the scientific community just took the same suite of tools they'd been using at other locations and used it on Acasta now. When the Jack Hill zircon that they developed, there's all sorts of tools, techniques. The geochemist toolbox is really, really big for the old zircons. When you find a new suite of zircons, which have just been discovered in South Africa, you can just take that same toolkit and apply it to those new samples. So finding new samples is... You do two things. You find new samples and you develop the toolbox. And those are two different sort of strategies to take when studying these old rocks. So, yeah. But you're totally right. The toolbox is focused on what did the ocean chemistry look like? Was there life at this time? Those types of questions, for sure.
Yeah. You know what we need to do at the end, Jesse, when we wrap this up, is we need to have a final image where we have like a chart of the Acasta, the Jack Hills, the Isua, and so on, and what are the important questions that each of those
that's a good idea.
Understanding
like
those rocks, what that can give us.
Yeah. I like that idea. That's a nice one. Yeah. Okay. Put a what's your phrase? Put a pin in it. Put a pin in that one, Chris, and we'll come back to it.
I didn't know that was my phrase. Apparently I have phrases now, Jesse.
You do have a lot of phrases. Yeah. Mr. Smudge over there has a lot of phrases.
Okay. All right. Man. That is not okay. That's not a name that's going to stick, Mr. Smudge. Jesse thinks I smudge everything with my dirty fingers.
You do. You're just a smudge factory over there, smudging everything you touch. All right, Chris. Hey, I think that's a wrap. You can find this with all the images that we talked about on our CampGeo mobile app, the Earth's Oldest Rocks visual podcast series there. It's available there with the previous 5 episodes that we've talked about other old rock locations, including Acasta and the Jack Hills. And we've got more coming this way. So, stay tuned. You can follow us on all the social medias. We're at Planet Geocast. Send us an email, planetgeocast@gmail.com. Visit our website, planetgeocast.com.
Cheers.